Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 43. Today we will look at some more examples of circuits that use op-amps in them, starting with an interesting example of applications of op-amps. But before we go there, let's refresh our memory about what we learned about op-amps last time. We said that an op-amp is a circuit, an amplifier, that has two inputs and one output. And the fundamental equation is that the output is equal to the difference between the two inputs multiplied by a certain gain. And A0 can be a large amount or moderate amount depending on the type of op-amp that we have. So then we came along and constructed some topologies of amplifiers using the op-amp as a building block. For example, we saw that we can build a non-inverting amplifier by dividing the output voltage and feeding it back to the inverting input of the op-amp. And this gave us a voltage gain for the overall circuit, which we call the closed loop gain, equal to 1 plus R1 over R2 if the gain of the op-amp is very large. Alternatively, we can create an amplifier like this, where a resistor connects from the output to the inverting input, and the resistor connects from the inverting input to the main input, and this gives us a voltage gain of approximately minus R2 over R1. The key property that we emphasized last time was that if the gain of the op-amp is very large and the output is moderate, then the difference between the two inputs has to be small. For example, here, if one input is 0, the other input will be close to 0. And that's why we call this node a virtual ground, because its voltage excursions are very small. So today, we'll take these ideas and go farther with them. But first, let's look at an application of op-amps in real life. So the application that I wanted to show you, example of application, is what we call a voltage regulator. So we are talking about voltage regulators. All right, well, remember that at the beginning of this course we built circuits that would take the line voltage 110 volts or 220 volts and bring them down and then rectify them to give us a DC, for example, as a laptop charger or a cell phone charger. So that's fine, we could do that. So let me quickly draw something like that. We had for example, a diode bridge. Before that we had a transformer. So at the primary of the transformer, we connected 110 volts or 220 volts. That gave us something here, maybe 20 volts. We rectified it, full wave rectified it, and gave it a capacitor. And then we used this to drive some sort of device. So some sort of equipment or device. Okay, so here we have a constant voltage with a small amount of ripple on it. So we went from AC at 110 volts or 220 volts to DC of, let's say, 15 volts. All right, now the problem is that this voltage that comes from the line, the mains, is not always constant. It may fluctuate, which means this voltage may fluctuate. And this device doesn't like so much fluctuation in that voltage. So oftentimes we add something else between this circuitry and this sensitive device called a voltage regulator. And the job of voltage regulator is to take a voltage that might vary to some extent, but produce a constant voltage from it, a very well regulated voltage. All right, so a regulator is like this. Here's a regulator, and we give it a certain voltage, DC for now, but this DC may not be constant. Sometimes it's over here, sometimes over here. And what we would like to have at the output is a relatively constant voltage. So this might be as a function of t. So even though the input fluctuates to some extent, of course within reason, we would like the output not to fluctuate so much. And this is called a voltage regulator. Okay, so how do we go about building a voltage regulator using the devices that we have studied so far? So I will give you an example. All right. Well, let's suppose that this is the output of the circuit, and this is the input of the circuit. Now, if this voltage wants to change, and I don't want this voltage to change, I have to have something between these two to control this voltage, right? Obviously, we need some sort of mechanism. So let's go ahead and use a MOSFET as a variable resistor between here and here. So here's a variable resistor that we connect between these 2 points. We know that a MOSFET can operate as a variable resistor if it is in deep triad region, meaning that the source and drain voltages are close to each other. And to vary this resistance, we can play with the gate voltage. The gate voltage goes up or goes down, the resistance changes. Okay, now somehow I have to measure this voltage and determine if it's the right value. How would I do that? Well, this voltage might be quite large, like 15 volts. So generally I would like to bring it down a little bit, attenuate it by some factor. That's not that hard, so let's just divide it down by some amount, so R1 and R2. So if I know how much voltage I want to have here, I know how much voltage I want to have here. Not a big deal, right? Okay, so here's a voltage. This voltage represents the output voltage with just a simple factor. These two are related. So if for some reason this voltage is going up, this voltage is also going up. Now, I need to tell this guy to adjust its resistance and hence adjust this voltage depending on what I'm measuring here. For example, if the voltage that I measure here is too high, then I have to tell this guy to increase his resistance so that we have more attenuation going this way and this voltage drops, and vice versa. So, how do I know if the output or this voltage is the correct value? I have to compare it with some sort of well-defined reference. So we have a reference here, which we call Vref. And this Vref can be generated by various mechanisms that we haven't talked about here. And what I do is I compare these two using an op-amp. And then I give the output of the op-amp to this guy. This becomes the simplest voltage regulator you can build. So let's see how this works. Let's say this is an NMOS device. So source here or here doesn't matter. And I have to choose this to be negative and this to be positive. Okay? All right. Now, for example, if the voltage that we have created here, after this rectification and capacitor, fluctuates up, if it goes up, this voltage wants to go up. If this voltage goes up, this voltage wants to go up. Now, if this voltage wants to go above a Vref, because we have a negative sign here, this voltage wants to go down. We have an inverting amplifier from here to here, right? If this goes up, this goes down. So this goes down. If this goes down, the resistance of this NMOS device increases. If the resistance increases, then we have more division between here and here. This voltage decreases. So this loop tries to regulate this voltage so that after everything is settled and everything is good, this voltage and this voltage are very close to each other. Remember the fundamental equation. We said if this gain is very high, these two are very close to each other. So assuming that the gain here is high, these two are very close to each other, meaning that this is close to Vref. If this is close to Vref, we know how much that is, right? So V out is equal to Vref This is Vref, close to Vref, Vref over R2 times R1 plus R2. So Vref times 1 plus R1 over R2, approximately. So long as this op-amp has a high gain, so long as this loop has a high gain, even though we have fluctuations here, this op-amp counteracts them by adjusting the resistance of this MOSFET accordingly. If this goes up, this op-amp increases the resistance, so that it goes down. And it constantly does that to make sure that this voltage is approximately equal to this, which means this output is approximately equal to this. So you want to have 15 volts, and let's say the reference is 3 volts. I choose this number to be 5. And I'm guaranteed to have a nice, stable voltage at the output. So that's a very popular use of op-amps in various electronic applications. Very well. Let's go to some other stages that we will study today using op-amps. We'll talk about a circuit called a unity gain buffer. So let me go over here and talk about the unity gain buffer. Now, to build the circuit, I'm going to start with the first circuit we studied, namely the non-inverting amplifier. So let's take a non-inverting amplifier, and we said that we have two resistors here that provide the division and feedback signal, it's the signal back to here, V in and V out, R2 and R1. So we said that the gain of the circuit, the closed loop gain of the circuit, if the gain of the op-amp is very high, is equal to V out over V in, approximately equal to 1 plus R2 over R1. Okay, now let's consider a special case where R2 over R1 is very small. In other words, R2 is maybe 0 and R1 is infinity, right? Let's consider the extreme case. So let's consider a special case where we have R2 is 0, a short circuit, R1 is infinity, an open circuit. So it's just like this. V in, V out. And given that R2 is 0 and R1 is infinity, I can say that V out over V in is equal to 1 approximately. This is what we call a unity gain, because the gain is 1, buffer. It's a buffer circuit. So again, you might be asking, what's the use of a circuit that has a gain of 1? A piece of wire would do the same thing. But the difference here is that this circuit has a high input impedance. Remember, when we look into an op-amp, generally we see a high input impedance. So if I attach this to some other amplifier, some other device, it doesn't load it. It doesn't want to draw current from it. So that's good. The question is, can this also drive a heavy load? Meaning, can it drive a low resistance load? And the answer is yes. And to figure that out, we're going to construct a Thevenin equivalent of this circuit and see what it looks like. So here's the situation. I have V in here. So what we know is that input impedance, oh, the pen decided to go crazy again. So input impedance is infinity, right? Very high. So that means can sense voltages without loading the circuit. So if I have some sort of circuit, some sort of device, and I want to take its voltage to the outside world, I can use this buffer, because this buffer will not bother that circuit. All right, but then Also, we would like to see what kind of output impedance we have here, because that determines how well we can drive a load out here. So let's construct the Thevenin equivalent. And for that, this is what we will do. First, let's find VTH. So VTH, meaning the Thevenin equivalent, or VThev, that's easy. VThev is equal to the voltage that we measure here when it's not connected to the rest of the world. Well, that's approximately equal to Vn. So that's fine. But now we need to find Rthev. And we know how to do that. We set all independent sources to 0. So this goes to 0. We apply voltage from outside and measure the current. But we need a model for this op-amp. How do I model that? Okay, well, we said that, for example, the 741 has an output impedance of 75 ohms. What does that mean? Well, let's try to construct a model for the op-amp. The op-amp wants to generate a voltage at the output. So, in a sense, I'm constructing a Thevenin equivalent for the op-amp itself. And that's what it looks like. So, this is V in 1. This is V in 2. This is A0 times V in 1 minus V in 2. So far, these represent this operation here, right? We generate a voltage at the output, which is equal to A0 times the difference at the input. So far, that's the ideal op-amp with a gain of A0. But then the op-amp may have an output resistance, so that's what we call, for example, R out. This entire circuit models one op-amp, one op-amp that you can buy, let's say 741. In 741, A0 would be 100,000, and R out would be 75 ohms. All right, now I am still trying to find the Thevenin equivalent of this whole system, right? So, and I have to set all independent sources to 0. This does not go to 0 because it's a dependent source. Okay, so now let's change the color to something else. Okay, so V in 1 is set to 0. That goes to 0. V in 2, the inverting input, is connected to the output. So that is connected to the output. Okay, and we need to find the Thevenin resistance. So we come from outside, apply a voltage Vx to this point, and let's call this ground so that the circuit is not too crowded, and measure this current Ix. This is trying to find the Thevenin equivalent resistance of this whole structure with this input set to 0. Okay, so that's not that difficult. V in 1 is 0, so that goes away. And what we have here is only A0 times minus V in 2. Now V in 2 is shorted to the output. So V in 2 happens to be equal to Vx. Right? So that's easy. So then what we can say is V in 2 is equal to Vx. And that means that this voltage is given by A0 times minus V in 2, so minus A0 times Vx. And now we just need to write the current of this R out. And we know that the only current that flows at this node is going this way because the input of the op-amp does not draw any current. So I can say that Ix, the current coming into here, is equal to the current through R out, going this way from right to left. And that current is given by this voltage minus this voltage divided by R out. This voltage is Vx, so it's equal to Vx minus this voltage. This voltage is minus A0 Vx. So plus A0 Vx divided by R out. So we can find Vx over Ix. Vx over Ix is equal to R out over A0 plus 1. That's a fascinating result. This says that even though when I bought a 741, just by itself, it came with an output resistance of 75 ohms. After I placed it in this configuration, namely shorting the output to the input, the resistance that now this presents to the outside world from here is as low as 75 ohms divided by 100,000. So the small signal output resistance of the unity gain buffer is extremely low depending on the values we start with, depending on R out and A0. And that's a very valuable property of the circuit. Not only its input impedance is high, its output impedance is also low. So a good buffer for voltages is exactly that. It can sense a voltage without loading the circuitry and can drive a low resistance because its output resistance is already very small. In other words, if I were to construct a Thevenin equivalent for this whole thing, it will look like this. V in R out over A0 plus 1, and then going to the outside world. So now you can see that even though I may connect this to, let's say, 10 ohms, I have very little attenuation from here to here because this resistance is extremely small. So we say this buffer is a good driver. It can drive a heavy load, a low resistance very well because its output impedance is low. All right, so that's the unity gain buffer, and it has some applications in cases where we need to drive a low resistance or we don't want to load the preceding stage. Very well. The next circuit we're going to look at is the integrator. This is along the lines of what I mentioned last time. We said back in 1940s, they were trying to simulate differential pairs, differential equations using op-amps. And differential equations, we have differentiation and integration and summation, etc. So naturally, they were looking for a circuit that can perform integration. You give it an input, it generates the integral of the input at the output. So an op-amp can do that, and that's very interesting. So let's go ahead and see how we can do that. All right, so before I introduce the integrator, I need to go back to the inverting amplifier and consider a more general case of that topology. So let's look at what I call general inverting amplifier. And by general, I mean the following. Remember that previously we had from the input a resistor going to the input of the op-amp, and then from the output a resistor going back to the input of the op-amp. We had one resistor here, one resistor here. Well, these don't have to be resistors. They can be other two-terminal devices. So let's just call these some general impedances. We call this Z1 and this Z2. And we would like to explore other options than resistors. Can Z1 be a capacitor, an inductor, a diode, all sorts of interesting things, right? So that's what we call a general inverting amplifier. That's what I call it. It's not a standard terminology. And we would like to consider a few special cases of this circuit. Now what we do remember is that if A0 is large enough, the gain of the op-amp, then we can say V out over V in is approximately equal to minus. Previously we said R2 over R1. But now, in the general case, we can say Z2 over Z1. This impedance Z2 over this impedance Z1. In a sense, this is the transfer function from here to here. It could be frequency dependent. All right, so let's take this, and now we go to build an integrator. So an integrator is pretty simple. We assume that Z1 is still a resistor like before, but for Z2 we use a capacitor. So here's what it looks like. And then we have ground at the non-inverting input. Okay, looks a little strange, but don't worry, we'll analyze it. Okay, so some basic observations. Again, if A0 is large, usually we start out with that simplifying assumption. Then we know that this node X is a virtual ground, because no matter what happens, as long as this gain is high and this voltage is moderate, then this voltage divided by this gain, which is the difference between these two, has to be small. So node X is a virtual ground. So that's good to remember. Okay, now I would like to find the transfer function of the system. And I don't have to write equations from scratch. I can just go back to this result and say V out over V in if A0 is large is equal to minus the impedance of the load that's connecting the output to the input, this impedance. Now you know from your basic circuit theory that the impedance of a capacitor is given by 1 over C1s. So 1 over C1s. And then for R1, we just have R1, so Z1 is R1. And you can see that this is now minus 1 over R1 C1s. If a system has a transfer function of 1 over S, that system is an integrator. Because you know that if you take the Laplace transform of an integral, you end up with 1 over S. So that's an integrator. So that's very cool. This circuit can integrate the input. If you give it, for example, a sine, it gives you a cosine, and so on. Also some interesting results. Okay, so we also see that we have a negative sign here. This negative sign doesn't bother us so long as we are aware of it, but it's not a big deal that it's a negative sign. And then, of course, we have R1, C1 as parameters that determine the scaling factor here. Okay, now what we did here, in a sense, is analysis in the frequency domain, because we found the transfer function of this integrator. But let's also analyze it in the time domain, because it gives us a better understanding of what is going on in the circuit. All right, so here's what we'll do. So forget about this equation, or this equation. Let's assume we know nothing about Laplace transforms. And we just want to start from basic properties of capacitors and resistors and op-amps and see what we get. Still assuming that A0 is large. Okay, well, let's do it this way. Because X is a virtual ground, the voltage at node X is very small. So I can say that the current through R1 is approximately is equal to V in minus Vx over R1. But Vx is very close to 0, so it's V in over R1. So we can say that current through R1 is approximately equal to V in over R1. In reality, it's V in minus Vx over R1, but because of the virtual ground property, we can say it's approximately equal to V in over R1. This, of course, also was true in the inverting amplifier that we studied last time. It's the same thing. Okay. All right. Now, let's go and look at this capacitor. We know the current through a capacitor, right? The current through a capacitor, if you remember, is in the time domain, current through a cap is equal to C dV over dt. We just have to be careful with the polarities of the voltage and the current and everything else. All right, so here we go. We look at this capacitor. We see that the current that's coming from R1 has to go through the capacitor. It has nowhere else to go because the input of the op-amp draws negligible current. All right. Now, can I write an equation for the current through the capacitor independently using this equation? Well, I can say that the voltage on the capacitor, derivative of that, times the value of the capacitor gives me the current. So let's try to do that. The voltage, let's assume that the voltage of the capacitor has positive on this side, negative on this side. It's up to you, but you can pick it like this. Then, if we calculate this, and V is chosen like so, the resulting current is flowing from left to right. That is the convention that we use. All right, so how much is the voltage from here to here? This voltage is 0. This voltage is V out. So this voltage from here to here is minus V out. So we will write minus V out. That is the voltage across the capacitor. Now take the derivative of that with respect to time, multiplied by the capacitor. That gives us the current flowing through the capacitor from left to right. And that happens to be the same as this current. So that's equal to V in over R1. And that means that V out is equal to, I'm looking for V out, the output voltage. So divide by C1 and a negative sign, and then integral of V in dt. So indeed, the output is the integral of the input. The input can be anything you want. It can be a time varying voltage or whatever, and the output is the integral of the input. Of course, anytime we take integrals, you have to worry about the initial conditions, etc. So those are always understood. But for now, we assume that the initial condition across this capacitor is 0. So we don't have anything C or all that stuff that you have to worry about here. Okay, so these two views are really one and the same. One in the frequency domain, one in the time domain. If you take the Laplace transform of this, you get that. You get the inverse Laplace transform of this, you get that. Okay, so let's look at an example based on what we have studied for the integrator and see what happens. All right, so here's a little circuit that we have here. And what we will do, R1, C1, V out, 0. I would like to apply a step to the input. So here's a step that goes from 0 to V0, a step of voltage. We assume the initial condition on C1 is 0, so it has no charge, no voltage. We assume A0 is large enough, and we would like to plot V out as a function of time. So let's try to do that. It might be good to plot the current through R1 first as a function of time, and then V out as a function of time. So here's what we have. For the input, we have a step. So the step jumps from 0 to V0. Okay. How about the current through R1? Well, remember, the current through R1 is just V in over R1. So it's also a step. So the beauty of this virtual ground is that it creates a current through R1 approximately proportional to V in and nothing else. So in a sense, we are performing a voltage to current conversion by this resistor. So the current through R1 is similar. It starts from 0 and jumps to some amount, which is given by V0 over R1. So this level is V0 over R1. This is the current through IR1, the current through R1 as a function of time. All right. Now this capacitor receives this current. We know that if we give a current to a capacitor, the voltage across the capacitor is the integral of the current. Right? This voltage is in the integral of this current divided by C. So this capacitor tries to integrate the current that's flowing from the resistor into it. And if we integrate a step function, what do we get? We are charging a capacitor with a constant current. So the voltage across the capacitor grows linearly with time. Now we have a negative sign that you must remember. So the voltage at the output will go like this. It starts at 0 here, V out, and grows linearly, but downward because we have a negative sign. So that's the operation of an integrator in response to a step at the input. It integrates, but it also multiplies by -1. All right, so I want to emphasize for you to understand that it is this virtual ground here that allows this voltage to be converted to a current. So to a good approximation, we can say that the current through R1 is V in over R1. Now this may seem obvious or trivial, but if I show you another example, you appreciate that this is a beautiful property that we have when we have an op-amp and with a high gain. So let me give you a quick side note so that you can compare. Imagine that I have a resistor and a capacitor only, R1, C1, and I apply step here, 0 to V0. This is V out. In this experiment, can I say that the current through R1 is just the input divided by R1? No, because this voltage is not fixed. As we allow a current to flow through R1 and it flows through C1, the voltage on C1, and meaning the output voltage, keeps changing. So we cannot say that the current through R1 is just V in over R1 because of this dependence here. And that's the beauty of the virtual ground. Because it pins this node too close to 0, when we apply a voltage here, this voltage is converted to current by this resistor. So that current is just V in over R1, approximately. Whereas we could not say that here. And that's the difference between this, which is a passive circuit without any op-amps, etc., and the use of an op-amp to create a virtual ground node. Very well. In the next step, we want to analyze this circuit again, but this time not assuming that A0 is very large, to see what happens. Right? So as I said, the op-amp gain can be as low as 50 or even lower, or as high as 100,000. So we have to decide if the gain of the op-amp is high enough, or if the system is close enough to this idealized situation. All right, so let's find the transfer function if A0 is not very large. Okay. All right, so we have to go back and write some equations more carefully, because we cannot say this voltage is very close to 0. It has a voltage, Vx, and then we have to write our equations accordingly. One thing that does hold is that the current going through R1 still has to flow through C1 in its entirety, because it has nowhere else to go. And another thing that holds is that this voltage difference times A0 is equal to minus V out. That's the general equation of an op-amp that always holds. So with these two principles, we can find the transfer function. All right, so let's start with the latter. What we know is that this voltage minus this voltage times A0 is equal to minus V out, right? Because it's in the inverting input. So if that's the case, I can say that Vx in reality, so let's change the color of my pen to distinguish. So if I have V out and I want to find Vx, I just need to divide V out by minus A0. So I can say that Vx is equal to minus V out over A0, because A0 times Vx, this voltage times this gain, is minus V out. All right. Okay, so that's the first principle we're going to use. So Vx is equal to minus V out over A0. The second principle is that this current is equal to that current. So the current to R1 is equal to V in minus Vx divided by R1. And Vx we know. So V in plus V out over A0 divided by R1. That is the current flowing from left to right in R1. And this current has to be the same as the current flowing through C1. The current flowing through C1 from left to right is equal to this voltage minus this voltage divided by the impedance of C1. So this voltage we have, Vx, so minus V out over A0 minus this voltage, which is V out, divided by the impedance of the capacitor, which you know is 1 over C1s. So we just have to find V out over V in. That is the transfer function in the general case. So you find V out over V in. It comes out to be minus 1 over, let's see what I have here. So we have 1 over A0 plus 1 over A0 R1 C1s. That is the closed loop transfer function of the integrator if the gain of the op amp is not very large. And you can see that if A0 goes to infinity, this goes to 0, this goes to 1, we're back to the idealized situation. All right, so what's interesting is the following. With an ideal high gain op amp, this is an integrator. And we know that because if you take the Laplace transform of this, we get this. But here it's not quite that, because we have S with a coefficient, but then we have something added to it. So yes, this is a pole that is no longer at the origin. Here we have a pole at the origin. If I set the denominator to 0, I see that that's true only if S is 0. So this has a pole at the origin. So we'll write that pole at origin. Whereas this one no longer has a pole at the origin. If I set this denominator to 0, it's a different place. So we say that pole not at origin. Okay, so now what is the big deal about being at the origin or not being at the origin? All right, well, let's take a step back. Look at this transfer function and ask ourselves what happens to this transfer function as the frequency of operation becomes smaller and smaller. We see that this gain, if you want to think of it as gain, becomes larger and larger. Don't worry about the negative sign. So if S goes to very, very small values, the gain of the circuit goes to very, very high values. And it's unbounded so long as A0 is very, very large. On the other hand, here, if S becomes smaller and smaller, the frequency of the signal becomes smaller and smaller, then eventually this disappears and we end up with only A0. So the gain is not unbounded. The gain has a certain limit. So that's the distinction that we draw between this and this. Of course, this is the realistic picture, and that tells us that the pole is not at the origin. Okay. So let me check here and see what else we have. All right. Now, I would like to give you a cautionary note so that if you try to build an integrator in the lab, so this integrator does not work in the lab. All right? So even though I went through all the properties and analyzed it, everything else, and even though this is going back to the inverting input of the op-amp, as we stipulated before, this circuit still doesn't work in the lab. So you have to wait until the next lecture or the lecture after next lecture to see why the circuit doesn't work and how we would try to fix it. But I want to warn you that if you just go to the lab and take an op-amp, put this around it, connect to a power supply, it won't work. All right, so keep that in mind, and let's go to the next stage, next type of circuit. Well, the next type of circuit we will study is a differentiator, again along the lines of creating mathematical operations. We could look for a circuit whose transfer function is a differentiator. The output is the derivative of the input with respect to time. So let's see how that can be built. So differentiator. Well, we go back to this general situation and consider another special case. This time we assume that this is a capacitor and this is a resistor. So here's what we have. One capacitor going from the input to the virtual ground, and then a resistor going from the virtual ground to the output. And of course this has to be the inverting input, this has to be the non-inverting input, and this is the output. So I claim that this is a differentiator. So again, if I assume that the gain of the op-amp is high, we can use this equation and see what we get for the transfer function. So here's what we get. V out over V in is equal to minus Z2. Z2 is just R1, so that's easy. And then divided by Z1, which is just the capacitor. The impedance of a capacitor is 1 over C1s. So that gives us minus R1 C1s. So that's a differentiator, because we know that if we take the Laplace transform of this, we get the derivative with respect to time. So that's good. We can build a differentiator. Of course, we still have a negative sign, but that doesn't bother us. So that's an interesting circuit. Now that we have this little differentiator here, we have this little differentiator here and this little integrator here, I would like to draw some other interesting characteristics so that we can compare. So let me change the color again, go back to red. Okay. So let's plot the frequency response. This is something that you have learned in basic circuit theory. And to plot the frequency response, what we do is we replace S with j omega, pretending that the input is a sinusoid. We take the magnitude of this and then plot it as a function of omega. So for the integrator, this is what we see. For the integrator, so V out over V in magnitude as a function of frequency is 1 over R1 C1 omega. So it goes like this. It's a parabola. It's a hyperbola, right? Okay, so that's for the integrator. We said that as the frequency of operation goes to lower and lower values, the transfer function goes to infinity. The gain goes to infinity. Okay, how about the differentiator? Same thing. We replace S with j omega, take the magnitude, so j goes away. We have R1 C1 times omega. So for the differentiator, we have something like this. So again, V out over V in magnitude as a function of omega, that's just like this. So this is the differentiator. Okay? All right, so what we see is the following. An integrator amplifies low frequencies and attenuates high frequencies. A differentiator attenuates low frequencies, amplifies high frequencies. All right, this is the behavior in the frequency domain. All right, the fact that the differentiator amplifies high frequencies is generally troublesome. What it does is, if we have noise in the system at high frequencies, it amplifies, even though we're not interested in noise. And for that reason, which is a little beyond the scope of this course, we rarely use differentiators. We try to use only integrators if we can, so as to avoid this problem of high frequency noise amplification. And for that reason, we won't study the differentiator in other cases, or when A0 is not very large and all these other things, because the integrator has much more application than the differentiator. All right. So we are ready to look at one more type of stage using op-amps that's also very useful. So let me add a page. And again, it goes back to solving differential equations. So we have integration, differentiation, and summation. We have all these terms that we have to add together. So this is what we call a voltage adder, or sometimes we call it a voltage summer. It sums the terms. So let's suppose I give you two voltages. How do we add them together? That doesn't seem very easy. In fact, there's a very simple application where we do need to do that. Imagine that you have, for example, a music band, a concert. Okay? So you have a guitar here being played by somebody, and there's a microphone that picks up this sound. And then you have, I don't know, a violin here, and there's a microphone that picks up this sound. So we generate a voltage here for the guitar, generate a voltage for the violin, and then all of these have to be, for example, recorded or given to speakers to be broadcast. So how do I combine these two signals? How do I add them? So these should go into something that adds these two voltages, right? In fact, in a general music environment, we even need more than that, because depending on the situation or the type of music, we may want to have a louder guitar and a softer violin. So not only do I want to add, I also want to be able to adjust how much of this voltage goes this way and how much of the voltage goes this way. In other words, I want to add the weighting factors to these two voltages. And this is what we call, in music, we call this mixing. This is in music industry, and we call this mixing. So you have these mixing boxes that you can buy, and you plug in different microphones from different musical instruments, and then you can adjust how these can be mixed, what weighting factors should be used for these different instruments. All right, so how do we build a circuit that can do something like that? And an op-amp gives us a nice, elegant solution. So here it goes. We take an op-amp, similar to the inverting amplifier topology. So here's the inverting amplifier topology with R, let's call this RF, V out, negative, positive. Now what I remember from the inverting amplifier topology is that if I have a resistor here and I apply a voltage here, then by by the effect of this virtual ground here, if A0 is large, so this is virtual ground, right? We said, due to this virtual ground, this voltage is close to 0 and doesn't change much, which means the current through R1, to a good approximation, is just V in over R1. We said that this topology is capable of converting V in to a current and letting this current flow through this RF to generate an output voltage. I repeat, this is so important. This topology with this virtual ground is capable of generating current through this R1, which is equal to approximately V in over R1. So it converts this voltage to a current and then lets this current flow through the feedback resistor, through RF. Okay, so in this topology, I have a current here approximately equal to V in over R1, right? All right, so let's do this. Let's call this V in 1. And let's add one more resistor to the same node and connect V in 2 to it. Now what happens? Well, again, because of the virtual ground that we have here, the current through R2 is approximately equal to V in 2 minus 0 over R2. So we have a current of V in 2 over R2 here. We have a current of V in 1 over R1. These merge here and flow through RF. So what I can say is the total current through RF, so current through RF is equal to V in 1 over R1. We converted the voltage to a current. V in 2 over R2. We converted another voltage to a current. And these two currents ended up flowing through RF. If I multiply this by RF, I find the voltage across RF. And because I'm interested in this voltage, I have to multiply by a negative sign. So I can say V out is equal to minus. You see, this current is flowing this way. If I multiply by RF, I get a voltage from here to here. But V out is from here to here. So that's why we have a negative sign. So minus RF times V in 1 over R1 plus V in 2 over R2. So that's a beautiful result. It says that the output voltage is the summation of two input voltages, the guitar music and the violin music. And depending on how I choose R1 and R2, I can give different weighting factors to these two. For example, if R1 is very large, I have less effect from V in 1, more effect from V in 2, and vice versa. So I can perform mixing with the type of music that I'm receiving. So this circuit is called a voltage adder or summer, and it has numerous applications in design. Very well. So this brings us to the end of this lecture, and in the next lecture we will look at some other applications of op-amps. I will see you next time.